Okay, so welcome to this video that is going to walk you through section 9.1 of the textbook. I'm assuming at this point that you have looked at section 9.1, especially the intro, and you have a basic idea of where we're headed with this stuff. Okay, so our chapter 9, ISU, is about redox and electrochemistry. You have to realize, in order to approach this unit, you have to make sure you need to recall the, sorry, I don't have a glove on and it's pushing me through things. There we go. Okay, we have to recall the difference between an atom and an ion. So Cl2 in the gaseous state is the elemental state. And this is actually its atomic state. When Cl minus is dissolved in, say, water, it's the ion. So ions typically have charges, and they have charges because they've gained or lost electrons. You should know the difference between an ionic compound and a covalent compound. So ionic compounds have transferred electrons to become stable. Covalent compounds are sharing electrons to become stable. You want to think a little bit about the types of chemical reactions: synthesis, decomposition, single displacement, double displacement. And we're going to talk a little bit about voltage and potential energy differences. And then the last thing that should kind of be familiar to you is something called a net ionic equation. And that's a sum of just the ions that are involved in a reaction, not the spectator ions that are not involved, that exist on both sides of the equation. So if you need to look at any of that, you can try section, the Are You Ready section on page 596 to work on that. Okay. Oops. Okay. After the discovery of the electron in the late 19th century, chemists realized that there was an entire group of important reactions, and those important reactions involved the transfer of electrons. So you and I are used to balancing reactions. If I said, x squared plus y gave you, I don't know, maybe xy plus y squared gave you xy, you would put a 2 in front of here. And to balance things for the number of atoms. There are 2 x's on the right, there are 2 y's on the left. But it turns out that there is a whole class of electrons for which you're not looking to try to balance the atoms, although the atoms should balance, and they will balance. But the number of atoms that you're actually going to balance is going to seem strange. And that's because you need to balance a certain number of electrons. So reactions will involve certain numbers of electrons. For these reactions, it becomes true that something in the reaction is going to gain an electron, something in the reaction is going to lose an electron, and the total number of electrons gained and lost are the same. So if something gains 5 electrons, something else will have to lose 5 electrons. So that's really where we're going with redox. This unit, the only thing, our real goal is to get you to understand what redox is and be able to balance a redox reaction and then predict if a reaction is going to occur. So if I dropped a penny in some nitric acid, would a reaction occur? Would something happen if copper was dropped in nitric acid versus copper was dropped in KMNO4 or something else? You should be able, based on the stuff that we're going to learn, to predict whether or not a reaction will occur. Okay, first thing you have to know is some basic definitions. The definition of an oxidation is the process where something loses 1 or more electrons. You can remember that with the mnemonic oil. Oxidation is a loss. It's a loss of electrons. Now, if something loses electrons, something else gains electrons. So, we have reduction. Reduction is the process by which something in a reaction gains 1 electron. I know it's weird. It's gaining an electron, but the word is reduction. So reduction is a gain. So you can remember the mnemonic oil rig. Another mnemonic that I learned is Leo the lion goes grr. Lose electrons is oxidation, gain electrons is a reduction. Okay, so we're going to look at what I mean by that. Now, a couple of more definitions. This is reducing agent. So something gets oxidized, something causes it to get oxidized. The thing that causes it to get oxidized is called the oxidizing agent. So if a substance loses electrons, it's gotten oxidized. What did it give its electrons to? It gave its electrons to the reducing or to the oxidizing agent. That causes the oxidation of something else. Now, interestingly enough, if it is causing something else to get oxidized, so it's causing something else to lose electrons, it's gaining electrons, and therefore the oxidizing agent actually gets reduced. And the reducing agent is oppositely the substance that causes an entity to get oxidized or to get reduced. So if it's causing something else to get reduced, so it's causing something to gain electrons, it itself is losing electrons. So the Ra loses electrons. That means it gets oxidized. And this is talked about on page 605 in the bottom right corner. Okay, so let's look at a particular example, and we can kind of base everything that we're going to need to know out of this section on this example. If I was there, I would take some copper wire, like in this picture right here, some copper wire, and I would call it Cu solid, so that's listed right here, and I would put it in a solution of silver nitrate. So we put it in some solution of silver nitrate, and we wait a few minutes. What starts to happen is flakes of solid silver appear in the beaker, and you see them growing actually on the copper wire. The liquid, on the other hand, starts turning blue, and that's because copper ions themselves are blue. So hopefully you realize that this is a salt and this is a salt. So I'm going to take this reaction, I'm going to break it down into all of its ions. Copper solid will just be Cu. I can put the solid. AgNO3 is going to be silver, which is 1 plus, and nitrate, which is 1 minus. There are 2 of those, there are 2 of those. And that's going to result in silver solid plus copper ions. Oops. Sorry about that. So our copper ions and our nitrate ions. I'm just going to squeeze those in right there, 1 minus, and there are 2 of them. So I've just essentially broke this down into its ions and broke that down into its ions. Now, see that there are 2 nitrates on this side. Let me change it to blue. There are 2 nitrates on this side, and there are 2 nitrates on that side. Those ions are common on both sides, so we usually don't include them in what we call our net ionic reaction. Copper solid is on the reactant side, but there's no copper solid on the product side. The only copper is an ion. That's different, so they can't cancel out. There's silver ions on the reactant side, but silver solid on the product side. So overall, we end up with this. Cu solid plus 2 silvers gives me silver solid and copper 2 plus. Okay, so this is what we call our net ionic equation for this particular reaction. So let's look at copper. going to copper 2 plus. For copper to go to copper 2 plus, it had to lose an electron. In fact, it had to lose two electrons because it went from copper neutral, copper atom, to 2 plus. So it's lost 2 electrons. So if it loses 2 electrons, is it an oxidation or a reduction? Hopefully you said it's an oxidation. And so notice how I've written this. This is often how you identify what's called half reaction. You identify the oxidation half and the reduction half. So let's figure out our other half. Silver goes from silver plus 1 to just silver. I forgot that there's a 2 there and a 2 there. So silver, it's going from plus 1 to neutral. So it had to gain 1 electron per every silver atom. So that's 2 electrons total. And if it gained electrons, it's a reduction. So we've identified in this 2 what we call half reactions. And the one thing we did not write in them is the actual electrons. So let's look at that. Copper, Cu, goes to Cu2 plus. It lost 2 electrons. So that means 2 electrons were given off from the copper solid. So the electrons end up on the product side. This reads as an oxidation. This is called the half reaction. That's the oxidation half reaction. Now the silver half reaction is like this. So silver 1 plus to solid silver, and we had 2 of them. In this case, we needed to gain 2 electrons. So those gain electrons go on the reactant side because we gained those 2 electrons, and that's the reduction. A couple of hints here for you to notice. The charge total on the reactant side equals the charge total on the product side. So on this copper side, the sum total is 0. And on the product side, 2 plus and 2 minus is also sum 0. On this reactant side, 2 positive ones and 2 negatives from the 2 electrons is a sum total of 0. And this silver has a sum total of 0. So it's another clue that we're right. These are called the 2 half reactions that make up this redox reaction that you're seeing in this particular example. So this is a slide where if I needed more room to write out their half reactions, I would have written them here, but I wrote them on the previous slide. So you can pause right now and you can try to write out these half reactions yourself. Include the electrons transferring and include which side is the oxidation, or which half reaction is an oxidation and which half reaction is a reduction. Now, just so we kind of see what's actually happening, on the piece of copper metal that would be in this solution, this is a piece of copper metal. And of course, there's a solution all around it. And that solution has these silver ions dissolved in it. Copper is going to lose 1 electron to the silver. And it's going to turn copper into a positive ion. So the copper ion essentially floats free. This is blue. Meanwhile, copper loses 1 electron to this Ag+, and that Ag+ forms a solid on the surface of the copper. It loses a second electron to another Ag+, and that starts building up on the surface of the copper. So 2 things will start happening. The silver will start to build up on the surface, and the copper will actually start to break down. So eventually this reaction will stop when you've run out of copper metal. And so this particular copper wire will eventually completely break down if there are enough silver ions to take all of its electrons. So I can show you an example of that. just sharing a different screen. 1 second. Here we go. Trying to get it to share. Okay, so now that we've seen that video, hopefully you can answer some of these questions. So you can pause it right now and you can try to answer these questions. And I will go ahead and answer them. Electrons are transferred from neutral, excuse me, I just forgot what I was doing, neutral atoms to charged ions. Copper atoms undergo, so the copper went from copper solid to copper 2+. So it lost electrons. So lose electrons is an oxidation. So they undergo oxidation because they lose electrons. Silver ions undergo reduction because they gain electrons. Okay, so here's a couple of questions. This is right out of the textbook from section 9.1. Okay, this is the first practice problem. I just cut them right out of the textbook. This happens to be page 601 and 602. Let's just try A and 4 down here. We can make sure we know what we're doing. It says write the oxidation and reduction half reaction equations for the following redox reactions. So I've got SN2+ plus CO yields SN plus CO2+. Just for the sake of simplicity here, I'm not going to include the subscripts of the aqueous and the solids because we have it right here. So you can see it right there. So SN2+ goes from SN2+ to SN. So in order to do that, in order to get to 0 as its some charge, it's going to have to gain 2 electrons. So SN gains 2 electrons. And if it gains 2 electrons, so gain electron is a reduction. This is the reduction. Oops. So that's the half reaction. You would just write SN2+ going to SN, and you have to put the electrons on the correct side. So it's gaining 2 electrons. So you put them on the gain side. The other half of the reaction is cobalt to cobalt 2 plus. So cobalt here would lose 2 electrons. And so that would make it an oxidation. So the half reaction is cobalt going to cobalt 2 plus, and the 2 electrons are lost. So they are being given off. They are a product. And so this is your oxidation reaction. And this was our reduction reaction. Okay, so try that again for B and C.